Hello again, and welcome to another lecture on our series covering trigonometry. Last time we looked at the graphs of the sine and cosine function, and we kind of tweaked those graphs a little bit and saw some fairly complicated curves. Well, today I'd like to look at the remaining four trigonometric functions: tangent, cotangent, secant, cosecant, and briefly look at their graphs. You'll be surprised at what these graphs look like. They're kind of interesting. One of the things to keep in mind throughout today's lecture is the issue of periodicity. Once we know what a piece of these graphs look like, then we know the entire graph. All these functions are periodic in one sense. Okay. Let's recall the sine and cosine properties that we did last time, because they'll affect what we do today a little bit. Sine x and cosine x, the domains, all real numbers. The ranges -1 to 1. Sine's an odd function, cosine's an even function. They're both periodic with period 2 pi. The amplitude is 1 for these functions. Then we spent a lot of time changing the amplitude, changing the period, shifting them horizontally, and then shifting them vertically. And all of those involved more complicated expressions, but the bottom line is they all pretty much look like sine functions or cosine functions, just moved around a little bit. So let's now go to the tangent function. This is a neat graph. You'll like this graph. Let's see how to find out what it looks like. First of all, tangent is sine over cosine. So already I see a problem. The denominator might be 0. Cosine x could be 0, and hence the domain of the tangent function is not all real numbers. There are certain values of x you cannot plug into the tangent function. In particular, if you take x to be pi over 2, then cosine of pi over 2 is 0, and the tangent's not defined. So already we have something interesting, I think. It's not defined for certain x values. In a minute, I'll list those values for you. Tangent is also an odd function. Odd in both senses. It's kind of a weird-looking graph, as we'll see in a moment, and it's odd in the mathematical sense, that tangent of minus x is minus tangent of x. And you can see that by saying tangent minus x is sine of minus x divided by cosine of minus x. Then remember the numerator, sine of minus x, that's an odd function, so that's minus sine x, whereas the denominator is an even function, so cosine minus x equals cosine x. Pull out that minus sign and you have minus tangent x. So we'll have some symmetry here across the origin. What about intercepts of the tangent function? When will it touch the x-axis? Well, when the numerator is 0. And sine is 0 when x is 0, or pi, or 2 pi, or minus pi, minus 2 pi, etc. So how could we get the graph? Well, the most mundane way would be plot a lot of points. For instance, here's a nice point you could plot. When x is pi over 4, tangent of pi over 4, we did that earlier, that's equal to 1. Okay, so we could plot that point, we could plot the intercepts, we could do a lot more points. Here's the graph you get. What a good-looking graph. Don't you like it? I really think this is an interesting graph. This is the graph of the tangent function. Let's savor it for a moment. First of all, notice that it's symmetric about the origin. It's an odd function. How about those dotted lines? Those indicate the vertical asymptotes. At pi over 2, the tangent's not defined, and it has a vertical asymptote there. And in fact, the graph goes up towards positive infinity on one side and to minus infinity on the other side. What's the period of this function? Well, look, it's got these chunks, these pieces, and they seem to repeat. Well, one of them is from minus pi over 2 to pi over 2. That's length pi. And then it's repeated. So the period here is pi, not 2 pi like sine and cosine, but rather pi. Isn't that interesting? So it's a function with period pi odd with these vertical asymptotes. How many vertical asymptotes does the tangent function have? Wow, an infinite number of vertical asymptotes. So let's review some of the properties of this tangent function. Its period is pi. Its domain is all real numbers except those numbers where the cosine is 0. And the cosine is 0 at pi over 2, and then pi over 2 plus pi, i.e. 3 pi over 2, and then 5 pi over 2. And then you go the other way. You can go pi over 2 minus pi, which would be minus pi over 2. And we write this in the following compact form. Pi over 2 plus n pi. And n can be any integer. So that's a list of all the bad points. In fact, that is a list of all the vertical asymptotes. Look back at the graph. Pi over 2, vertical asymptote. 3 pi over 2, vertical asymptote. Minus pi over 2, vertical asymptote. You get the picture. What's the range of this function? Well, the graph kind of tells you. The range is all real numbers. This goes from the way down there to way up there. It goes from as far as you want, negative direction, up to as far as you want in the positive direction. Now, you remember last lecture we took the sine and cosine, which we were very comfortable with, and then we began to massage them. I'm not going to do too much of that. It's pretty complicated with the tangent function, let alone with the other functions that we're going to look at today. But let me show you a quick example of a modified tangent function, and we'll use some of the same techniques we did last time. What do you think the graph of tangent x over 2 would look like? Tangent of x over 2. Well, it's going to look like the tangent function, but the asymptotes will be a little bit different because the bad points, where the cosine is 0, have changed slightly. When x over 2 is minus pi over 2, that's a bad point because that's where cosine is 0. That means x is minus pi. So minus pi is now a vertical asymptote. In a similar fashion, when you have x over 2 equal to pi over 2, you get another vertical asymptote, and that yields x equals pi. So here's a graph of our tangent x over 2 function, and the only real difference is that the period is now 2 pi, because the vertical asymptotes go pi, 3 pi, 5 pi, etc. It's kind of been stretched horizontally a little bit, but it still looks like a basic tangent curve, doesn't it? All righty, good. I invite you to repeat that graph on your graphing calculator. Graph the tangent function, or the tangent of x over 2, on your graphing calculator. When you do that, you might observe something kind of weird. And here's what might happen. Let me look back at this graph. As the calculator is plotting points, it just plots the pixels. It just goes bloop, 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 bloop. Well, when it gets up to that vertical asymptote real high, it then jumps down to a very low point, and it might connect them, which it shouldn't do. It shouldn't cross the vertical asymptote, but it might connect them. And that would give you sort of a misleading graph. One thing you can do to avoid that is put your graphing calculator into something called dot mode rather than connected mode. In dot mode, the calculator just puts in the dots. In connected mode, it puts in the dots and connects them. And hence it might connect dots that shouldn't be connected. And this is true of all the functions tangent, cotangent, secant, and cosecant, because all 4 of these functions, as we'll see, have vertical asymptotes. What about the cotangent graph? How is it going to behave? We're comfortable with the tangent graph, an interesting graph. What about cotangent? Well, I'm not going to dwell on cotangent, but let me give you some of the features. It's cosine over sine. So the problem here will be when sine is 0. That's going to be division by 0. And sine is 0 when x is equal to 0, pi, 2 pi, 3 pi, etc. And we write that as x equals n pi, where n's an integer. Those are the vertical asymptotes of the cotangent function. This is also an odd function, and this will decrease on each piece rather than increase on each piece. The period again will be pi, like the period of the tangent function. Here it is. Here's a picture of cotangent. Notice the vertical asymptote at x equals 0, also known as the y-axis, and then the next one is over at pi. That's the next vertical asymptote. And notice that at pi over 2, the graph touches the x-axis. That's because cosine of pi over 2 is 0. The numerator is 0. Students might ask you, Professor, I want to graph this on my calculator to verify this picture. And I've looked on my calculator. There's no cotangent key, is there? What would you say to that student as a teacher? Help, help, how do I graph cotangent? There's no key on my calculator. Well, cotangent is the reciprocal of tangent. So all you have to do is graph 1 over tangent, and bingo, you'll get the graph of cotangent. Let's turn to secant x. Okay, what can we say about secant? Let's savor this graph for a moment. Well, let's see. Secant is 1 over cosine, and I already see some problems. For some values of x, secant will not be defined, will it? When cosine x is 0, we're in trouble. In fact, there'll be vertical asymptotes again. And that occurs, just like with the tangent function, at pi over 2 plus multiples of pi. Pi over 2, 3 pi over 2, 5 pi over 2, and then the other way. So we have vertical asymptotes. Those points are not in the domain of the secant function. All right, let me ask you this. What are the x-intercepts of the secant function? Where does it cross the x-axis? Trick question. It never does. Why not? Well, secant is 1 over cosine. And if that's ever going to be equal to 0, the numerator has to be 0, doesn't it? And 1 is not 0. So the secant function is either above the x-axis completely or below it, but it never crosses the x-axis. So it has no intercepts. All right, let me show you the graph of secant, and I'm going to graph it together with cosine because there's a really nice interplay between these two graphs. In fact, if you're comfortable with the cosine graph, you'll be equally comfortable with the secant graph. Watch how they go together as kind of a team. Cosine is yellow here, and notice that it's when x is 0, the y value is 1. That means that secant is also 1 there because the reciprocal of 1 is 1. All right. Notice that at pi over 2, cosine is 0, isn't it? At pi over 2, cosine is 0. That means secant is not defined there. So secant has a vertical asymptote at pi over 2. In other words, the zeros of the cosine function are the vertical asymptotes of the secant function. Okay, and you get this nice little picture. The green secant function is kind of interesting looking. It kind of looks like a bunch of parabolas, doesn't it? But those are not really parabolas because a parabola would open up forever. These are kind of, I don't know what you would call them, but they go up and hug their asymptotes. And then there's a chunk down there at the bottom, and then another chunk there. And they sort of go back and forth with these chunks like that. Okay, so that is the secant graph. And again, it's kind of based on the cosine graph. What about cosecant? How could we graph cosecant? Well, I think you got the picture, don't you? Same technique. It's 1 over sine. Uh-oh, sine can be 0 sometimes, can it? At multiples of pi. 0, pi, 2 pi. So those will be the vertical asymptotes. And here we've drawn a similar graph to the previous one we saw, but now I've shown sine x, our old friend sine x, goes through the origin. It's an odd function. it touches at pi, it touches at 2 pi, etc. And then I've drawn cosecant x. And notice how it comes down and kind of kisses the sine function at various values. It kisses it when x is pi over 2, because sine of pi over 2 is 1, and so is cosecant of pi over 2. At pi, sine is 0, so cosecant has a vertical asymptote. So I feel comfortable with secant and cosecant because I'm comfortable with cosine and sine. And then tangent is sort of, well, tangent and cotangent, memorize the picture of tangent. That's kind of an important graph, and we'll be using it a few times in this course. Let's do an example. Let's massage, say, the secant function a little bit and see how you can get a picture of an altered secant by studying the corresponding altered cosine. So let's compare the graphs of cosine 2x and secant 2x. Another way of phrasing this problem would be, how would you graph secant 2x? Well, here's how I would do it. I would first graph cosine 2x and then kind of paste the secant graph to the cosine graph. So let's look at this. Let's look at cosine 2x. F of x equals cosine 2x. What's the amplitude? 1. Is there any horizontal shift? No. Is there any vertical shift? No. The only thing that's changed here is the period. And the period is 2 pi over b, which is 2 pi over 2. That 2x is indicates the period. So the period is now pi. Instead of period 2 pi, it's shrunk down to pi, 1 cycle in pi. Here's some values. F of 0 is 1. Cosine of 0 is 1. And then f of pi is also 1. We're back to where we started from in one period. All right. What's the corresponding conclusion for secant 2x? G of x equals secant 2x. Well, g of 0 will be 1, just like cosine was 1, and g of pi will be 1. So now we can graph them together. The yellow graph is our old friend cosine with a different period. So it starts at 0, 1, and it does a full period, and at pi, it's back to where it started from, at pi 1. The period is pi instead of 2 pi. And then you paste on the secant pieces. The secant will be at 0, 1 and go up. It will have asymptotes at pi over 4 and 3 pi over 4, etc. How do you get those asymptotes? Well, if the cosine is ever 0, then you've got an asymptote for the secant. And notice that the yellow graph is 0 at pi over 4. So that must be a vertical asymptote for the secant function. Again, a nice interplay between secant and cosine, and the same kind of dance would be between cosecant and sine. Okay, you be the teacher. We sort of alluded to this a little bit earlier, but it's fun to be the teacher. You're standing up there teaching trigonometry, and a student comes up in panic because the student bought a calculator that's incomplete. It only has the sine, cosine, and tangent buttons on it. Teacher, where's my cotangent button? Where's my secant button? Where's my cosecant button? What do you tell the student? Relax. You can calculate cotangent as 1 over tangent. And in the same way, secant's 1 over cosine, cosecant is 1 over sine. So you really need just 3 buttons on your calculator to get all 6 functions. Thank goodness. All right, let me turn now to a topic that really is a calculus topic, but it involves functions that we've learned to love so far in this course. So I thought I would bring these functions together, play with them a little bit, but I'm going to couch some of the terminology in the language of calculus. Now, don't panic. I'll make it clear, I think, of what I'm talking about. We're going to look at an interesting combination of the sine function with an exponential function. We're going to glue them together and analyze the graph. So let's look at the graph of f of x equals e to the minus x times sine x. So sine x I know about, up and down, up and down, up and down. What about e to the minus x? Well, it's a decaying exponential, isn't it? As x gets bigger, e to the minus x tends to 0. So it's a decaying exponential. What will the graph of this product look like? Well, here's a picture of it on a graphing utility. This is the graph of e to the minus x sine x. Now let me sort of explain what's going on here. These are used a lot in engineering in the following scenario. The sine function's going up and down, like a harmonic motion, a spring going up and down. But suppose there's friction. So the amplitude starts shrinking. It gets smaller, it tires down, and it stops moving. So this would model some kind of behavior where the amplitude gets smaller and smaller. The e to the minus x term brings it down towards 0. Now, why does it have that horizontal asymptote at 0? Well, look what happens when x is really big. When x is really big, sure, sine x is between minus 1 and 1. That's okay. But the e to the minus x, when x is really big, imagine x, say 1,000, that's e to the minus 1,000 power, or 1 over e to the 1,000. That's an enormously small number, tiny number, 1 over e to the 1,000. And that's why the product shrinks down towards 0. All right, so this is an example of what we called damped harmonic motion. There's friction involved. You can illustrate this on your graphing utility. If you graph the following 3 functions, you'll kind of see a pretty picture. Graph e to the minus x sine x together with 2 other functions, e to the minus x and minus e to the minus x. And you should get a picture somewhat like this one. And you see here how e to the minus x sine x is inside a sandwich. The sandwich is, the top piece of bread is e to the minus x, and the bottom piece of bread is minus e to the minus x, and the function's kind of in between those two. Kind of neat, isn't it? So, what's the calculus language for what we just talked about? Let me throw a calculus, some symbols to you, a calculus equation. And you'd see this if you took a calculus class, but I think you'll understand it right now. Here's what we just observed. As x gets really big, the expression e to the minus x times sine x gets closer and closer to 0. It has a horizontal asymptote at 0. Here's how you would write this in a calculus textbook. The limit as x approaches infinity, that means x getting larger and larger, of the function e to the minus x times sine x equals 0. Okay? That means that as x gets larger and larger, that product gets closer and closer to 0. Okay, that's what that notation limit means, L-I-M. We'll see that notation again in a moment. Here's one of my favorite functions of all time. I love this function. Students love it too, I think, because it's got a bizarre picture. It's the function sine of 1 over x, not sine x, sine of 1 over x. Let's look at a picture of this function. Get out your graphing calculator, and I'm going to graph it on the interval minus 2 to 2. And then the height, the vertical window, I'm going to go say minus 1.5 to 1.5. I know the amplitude is still 1, isn't it? There's no number in front of the sine. So it's going to go between minus 1 and 1. And then I have a certain x interval. And here's a graph of it. Whoa, what's going on here? Let me try to describe it. I mean, this is bizarre. As x gets near 0, this function goes up and down between minus 1 and 1 infinitely often. It goes crazy. It just goes like this forever. Infinitely often. Notice that it's not defined when x is 0, is it? It's not even defined at 0. But as you get really close to 0, if x is like 0.00001, it could be some number between -1 and 1, and it keeps going up and down. Well, you might say, wait a minute, Professor, you have this plotted on a pretty big interval, -2 to 2. How about if we plot it on a smaller x interval? How about -0.01 to 0.01? We'll do that. You'll get basically the same picture. It'll look crazy. In fact, as you magnify in, it has that same behavior going up and down infinitely often. What would we say in terms of that limit notation? Is this function settling down to a single number as we approach 0? It's going back and forth, up and down. It never settles down, does it? It won't have a limit there, and I'll show you the notation in a moment. But before I do, let me modify that function. Let me put an x in front. So now it's x sine 1 over x. What do you think's going to happen now when I graph it? Okay, sure, the sine part's going to go up and down, go crazy as you get nearer and nearer to the origin. But there's an x in front. And when x gets near 0, that thing in front gets near 0. So I have a product of something between -1 and 1 times something that's going closer and closer to 0. The product will actually get closer and closer to 0. Here's a picture of x sine 1 over x. I've modified it with an x. We can use that language. I've dampened the function, haven't I? I've dampened it. Its amplitude is kind of getting smaller and smaller. Now it does have a limit. Now it's getting closer and closer to 0. Even though it's not defined at 0, you can't divide by 0 in mathematics, it's getting closer and closer. Here's the calculus notation. You can write this down and impress your friends who have never taken calculus. The limit as x gets closer and closer to 0, and you indicate that by x arrow 0, of sine 1 over x does not exist. That just means that there's no fixed number that it approaches. It just goes back and forth. It doesn't settle down. However, x sine 1 over x, as x gets nearer to 0, approaches 0. It gets very, very close to 0 as you want. So we write that the limit is now equal to 0. Let's do an application. Okay, an application of trigonometry again. We've explored some calculus applications. Let's step back and do an application of trigonometry now. This is kind of a fun, easy application. Here's the scenario. You have a plane flying overhead. And let's assume the plane is always 5 miles up in the air. And on the ground, there's a radar station. And it's tracking the plane. And in fact, the plane might be far away, and then the plane comes overhead and goes off that way. Here's a picture of the scenario. The height of the plane is always 5 miles. And there's the radar station over there. And the radar station is making an angle x with the horizontal up to the plane. And d is the distance between the radar station and the foot of the plane, the point perpendicular to the plane's position. So that sort of forms a right triangle there. And here's the question. If d is the ground distance from the antenna, from the radar station, to the point directly under the plane, as indicated in that figure, and if x is the angle of elevation to the plane, the angle as labeled in the picture, can we write d as a function of x, the distance as a function of x? Let's do that, and then we'll notice the picture that results from this. Well, look at the setup. Can you write d as a function of the angle x? Well, what's the cotangent of x? Cotangent is adjacent over opposite. Remember, tangent is opposite over adjacent, so cotangent is backwards. So it's d over 5. So cotangent is d over 5. Multiply by 5, and you have d equals 5 cotangent x. What's the domain of this function? Well, the angle x might be close to 0, so x is bigger than 0, and it goes up, and finally it might be pi, or 180 degrees, but of course we're using radians now. And in particular, at pi over 2, let's see, what's cotangent of pi over 2? That's cosine pi over 2 divided by sine pi over 2. 0, isn't it? Cosine is 0, sine of pi over 2 is 1. So the distance d is actually 0 when the plane's overhead, and that makes sense. Look at the picture. The plane is moving towards the radar station, and ultimately the distance d is 0, and then it grows the other direction. Here's a picture of 5 cotangent x. It's on the interval 0 to pi, and notice that at pi over 2 it crosses the x-axis, and that's because at that point the plane is exactly overhead. And notice the shape of this curve. It looks like our old friend, the cotangent function, doesn't it? Except it's got a 5 in front. Okay. I think we're kind of at a point where we're comfortable with graphing trigonometric functions. And the next time I'd like to sort of shift gears and use some of those skills of inverse functions that we developed quite a while ago to develop what are called the inverse trigonometric functions. Now here's a surprise. Not one of those trigonometric functions we've looked at is one-to-one. Not one of them passes the horizontal line test. So to define the inverses, we're going to have to restrict the domains of these trigonometric functions. So it'll be a fun lecture because it's got some interesting complications. Again, these functions will be on your calculator. So next time, I look forward to taking our knowledge of the trigonometric functions and developing the 6 inverse trigonometric functions. See you then.